will be. And I really would. I wouldn't have as much fun if I were calm. And it's all about me having fun, y'all. It's not about y'all. It's about me. Just kidding. All right. So yesterday we talked about the unit circle equation. You better write this in your notes. Okay? What is that equation? Rock on. Very good. Okay? X squared plus y squared equals 1. For kicks, to review from yesterday, I want you to do this problem. The point this ordered pair, this point, blank root 3 over 3, is in quadrant 2. I want you to find the x coordinate, bless you, for the ordered pair. I want you to do that now on your own. So let's check this out. What's the only thing I have at my disposal? My formula, my equation, x squared plus y squared is equal to 1. I have the y value, so I'm going to plug it into the y, and it's going to help me find the x value. Do you guys agree with that? Okay. Now, here we go. Let's think about what we have. X squared plus root 3 times root 3 is plain old 3. 3 times 3 is 9. And you know, you saw yesterday, I know it can be reduced. Don't do it. You're just going to cause yourself extra work at the end. I have to think of my 1 as 9/9. Do you guys agree with that? And now I can subtract my 3/9, which is going to give me 6/9. And now what? Square root of both sides, because we're solving for x and not for x squared. When I do this, it's going to give me the square root of 6. Oh, what's it going to give me? Plus or minus. Don't forget about that. Over plain old 3. Do you guys agree with that? Do I keep both of those? No. Why, Kayla? The one for x. Why? Why is it negative? Quadrant 2, which is here. Okay? That means it's going to be a negative positive. So I'm going to keep the negative root 6 over 3. Was it root 3 over 3? Yeah. Please don't think just because you have the correct two values that you don't need the parentheses. And I know that's kind of being nitpicky about it. But folks, it's part of an ordered pair. And an ordered pair has to be contained within those parentheses. So please use those. I know that's kind of silly for me to even say. But you'd be surprised what I see when I grade things. How many of you have on your paper negative root 6 over 3 for your x value? No, why not? 2 is not a perfect square. You only want to think what perfect square will divide into 6. 4 won't, 1 will, but it's pointless. Okay? You have to think perfect squares. Yes? You're just going to have to rationalize. You would have had, what, 2/3? All right, then you would have taken the square root, and we would have had this, Jansen, and you'd have had to rationalize, which is still going to give you root 6 over 3. Your work comes at the end where it's really extra work. Because I'm able, tell me why I leave this as 9. Because it's a perfect square. I know I'm going to have to go back and take the square root of it. Okay? It's okay if you do that, though. Totally fine. As long as you get it right, I don't care. You know that. Okay? Other questions? Facile or difficile? Facile. Well, let's move on. All right, check this out. We are going to think of these ordered pairs. The ordered pairs on the unit circle are called terminal points. The ordered pairs. And you remember in Algebra 2 we talked about how there were several different names for solutions, which were also called x-intercepts, which were also called roots, which were also called zeros, and we went through that a lot, almost every single day. This is the same thing. If I tell you to graph an angle and give me the ordered pair, it would be the same as me saying, what's the terminal point for this angle? Which means, or translates to, what's the ordered pair for this angle? Okay? But it's called terminal points. The thing you need to know about it, the terminal point, is sometimes called the terminal point T. It's sometimes called T. It'll always be a real number. Not going to be a pi thing or an I or nothing like that. It's always going to be a real number. And the terminal point is the ordered pair for the rotated angle for where the rotated angle lands or ends up. And if I think of terminal, the word itself, terminal, just using context clues, terminal, I either think of a terminal illness, which means at the end, or a terminal for an airport, somewhere that you have to go, okay? So I kind of keep that in my head because what I mean is if I have my unit circle, okay, my angle, and I'm going to tell you this all in a little bit, but your angle is always going to start here on the x-axis, and it's going to rotate up. And wherever that angle lands, this would be the terminal point. Okay? Now, rotate. Folks, if I start all rotations, put this right here. All angles, rotations start at the x-axis. You need to know that. You need to be writing this down, not just looking. All angles, rotations start at the x-axis, and it ends up being on the positive side of the x-axis. Now, what I want you to do, because I know we drew this little, we got to draw some things within this. So we're going to make a big O. Y'all know how I am with the big O. I need you to draw a big O unit circle. Mine are never going to be perfect. Never, ever. We talked about the unit circle yesterday. Its center is the origin. We also said one other thing. What's that? The radius. We also learned yesterday that the radius of the unit circle is what? It's always 1. It's always 1. And they're always congruent to each other. Okay? Now, what if I said, all right, well, what's that terminal point there? Think. What is it? It's 1, 0. How'd you get 1, Jansen? Because if the radius is 1, the distance over there to that terminal point is 1. Very, very good. Then, use that same thinking, y'all. What would the terminal point be for that point all the way at the top of the y-axis? 0, 1. Ooh. What's it going to be over here? Negative 1, 0. Now, I want to ask you something. Can distance be negative? Can I drive negative 14 miles? No. So if distance can't be negative, why is that 1 negative? Say it again. Because I'm showing the placement. And it happens to be on the side of the y-axis that those x values have to be negative, right? It's in between the second and the third quadrant, and the x values over here have to be negative. Do you guys agree with that? So what's this one down here at the bottom? 0, negative 1. Folks, you just discovered your first 4 critical points on the unit circle. Now, we talked about rotation. So all angles rotation start at the x-axis. So they all start right here. Just want to throw this out. If it rotates up, do you think that would be a positive or a negative angle? Come on, common sense. Positive. So if our angle is greater than 0 or positive, that's going to be a positive angle in degrees or whatever. If it rotates downward, I've already put it up here, then the angle will be what? Less than 0, which means negative. And doesn't that just make sense? That just should make sense. If it rotates up, it's positive. If it rotates down, it's negative, right? Now, I just want you to make this notation. If it's a positive angle, you got to know that we rotate up. And if it's a negative, it rotates down. Just make that notation in your notes. Notation in your notes. Kind of redundant. All right? Positive angle rotates up. Negative angle rotates down. We've never dealt with negative angles, have we? But now we're in this trigonometrical information, and we are going to deal with it. Okay? Very simple. Very simple. Here we go. How do we determine? How do we determine the distance of one complete revolution? How do we determine this? Folks, in geometry, what do we always tell you your calculator had to be in? What? No, in geometry. Degree mode, right? Up until now, we've dealt in degrees. Guess what we get to explore now? That other one that always gave you the wrong answers in geometry. Radians. In trig, we start working with radians. And folks, that's what we're going to think about here when we're talking about a revolution around that unit circle. It's going to be that in radians, okay? Now, degrees and radians are nothing more than different ways to express the same angle, Just like, and I've used this example before, 4 quarters and a dollar bill, still, they look different, still have the same value, right? That's the same thing with degrees and radians. It's just a different way of thinking. And we're going to use radians a whole bunch. Now, circumference. Do you agree circumference talks about the distance around a triangle? The distance around a circle? Yeah? Okay. So we're going to be talking about circumference. Circumference helps tell us the distance around a circle. That's important to us. You're getting ready to discover something else. This is a class full of discoveries. Y'all remember the formula for circumference? Anybody? What? 2 pi r. Very good. Attaboy. 2 pi r. Huh. And we're not talking about just any circle. We're talking about the unit circle, right? We're talking about that special, the unit circle. What did we know about the unit circle that might help us in this formula? Ah, the radius is 1. R is 1 in the unit circle. We're getting ready to do a proof without doing a proof. What am I going to do with that 1? Ah, I'm going to substitute. So I'm going to substitute 1 in for radius. Folks, what's 2 times pi times 1? 2 pi. What do you think that means? Nope. Decimals are the devil. Devil. No, decimals are the devil. It is never, ever, ever going to be decimals. What is that? But what is the circumference? Nope. What is the circumference? Don't give me a value. Tell me what circumference is. It's the distance around the circle. What does that mean? Now this is going to be weird kind of substitution. But that means that the distance around which circle? The unit circle is equal to 2 pi radians. I will be John Brown. Looky there. Now, if you skate, board, or ice skate, then you would tell me 1 revolution is what? 1 rotation is what? 360 degrees, okay? And you would tell me that 2 rotations is how many degrees? 720. Some of you guys, because that's what you do and that's what you're used to, you'll say 360. Oh, I did 360, man. Yeah. Oh, I did 720. Whew. Big deal. Now we ain't talking about degrees, we're talking about radians. So now you can go, I did a 2 pi, man. I did a 4 pi. Suck it. No, that we are dealing with radians. So 1 complete revolution around our unit circle is 2 pi radians, which is equal to how many degrees? 2 pi radians is equal to how many degrees? 1 complete revolution, 360 degrees. We're going to go back and forth. We're going to think a lot in terms of degrees because that's the way our brains are kind of wired. But we're going to be dealing with these radians now. So, draw me another big old unit circle. We're going to put some information in it. Very important information. got to think radians, folks. Think radians. If I don't move my angle and it doesn't move at all and we don't rotate it at all, then how many degrees would it be? Let's think. Back at you, Q. 0, right? If it doesn't move, then it would be 0 degrees. Or 0 radians. And what's that terminal point, by the way? Oh, 1, 0. You're right. Okay. 0 radians is equal to 0 degrees, just saying. And if I were to go all the way around the circle, one complete revolution is equal to how many radians? 2 pi radians. Which is equal to how many degrees? 360. Now notice where I've placed these numbers. I've put them these places for reasons. 0 shows no rotation at all. My blue line showing all the way around, notice where I put 2 pi. It's underneath the x-axis because it's showing you that I've gone all the way around, okay? So if one complete revolution is 2 pi radians, then what if I only went halfway? What is it? 1 pi radian. Am I going to write, if I said 1x, do we really write out 1x? No. We're not going to write 1 pi, we're going to write pi radians. And just for kicks, pi radians is equal to how many degrees? 180 degrees. Do you see how this is all connected? I can tell you can figure this out. You're great. You guys are awesome. Oh, what's the terminal point for that one? -1, 0. Very good. Guess I'll put that in blue. All right. So y'all are a bunch of smarty britches. What if I only went there? Look what I did. From here to here. Half pi. Now I want to throw something out. There's a better way to write this. Can I write it like this? Doesn't 1/2 pi mean 1/2 times pi over 1? And then how could I make that neater, nicer, more compact? What's 1 times pi? Pi over 2. Oh. Pi over 2. Radians. Hey, how many degrees? 90. There we go. What's that terminal point, everybody? 0. Thank you, everybody. Out of class. What's that terminal point, everybody? 0. Out of class. Thank you. Are we missing any? Yeah, we're missing the one at the bottom. Please hear me. Please, 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 please. I wish I had another color. What did I just press on? Purple. What is it? It's 270 degrees, yes. All right, see, because it's easy to think in terms of degrees, isn't it? This is where it is 270 degrees. Okay, now I want you to think, and this is what I want you to hear me say, okay? You've got to begin thinking. I have said all along, fractions are your friends. Decimals are the devil, right? We're getting ready to enter fraction funland. or fraction form, but Funland is so much more fun. Have you ever been on a farm? Not fun if you have to work, okay? I don't think. But it's all good. Think, think, think. Fractions, fractions, hold that, don't say it. This is what I want you to think of. Here's 0. Here's 1/2 pi. Here's 2/2 pi, because 2/2 is just really what? 1. So what would this be? 3/2 pi. How am I going to write that? 3 pi over 2. You've got to think in terms of fractions. 3 pi over 2. No, we're not there on the pi over 4 angles yet. All we're dealing with, that's 3 pi over 2. Think about it again. This is, and you can do this in pencil. I wish I could. 1/2, 2/2, 3/2, 4/2. Because isn't 4 over 2 just really 2? And isn't 1 or 2 over 2 just really 1? Think in terms of fractions, and it will make your life so much easier for this unit circle. Folks, this is this much. Look up here. That much information that we're getting ready to put on this unit circle. We got that much information, and you just have that much. And you're going to memorize it, and you're going to know it. You're going to memorize it first, and then you're going to learn it, and it'll be with you forever. Because when I see you out with your grandchildren, and you are coming to visit your parent in the nursing home that's in the room beside me, I may call you out, Rachel, and say, what's a 90-degree angle? And you better tell me, yes, but you also better tell me over 2 radians, because I will do that, and you know I will, unless I really, truly go crazy. Okay? Now, some of you I'll see anyway. Now, what are we going to do with that? Think about it. It'll hit you in a minute. 1/2, 2/2, 3/2, 4/2. Think in terms of pi over 2. 1/2. Now, what are we going to do with it? You're going to find terminal points. Find the terminal points for the following angles. Folks, you're going to have to do this by drawing the rotation and then find the ordered pair. You'll see what I mean here in just a second. Okay? Draw the rotation, and then you're going to find the ordered pair. Here we go. Check this one out. The angle is 5 pi radians. Okay? We literally have to draw this thing out. Now, here's what I want you to do. Where does the angle start? All angles start where? Over here at 1, 0, right? They all start there. But folks, come closer in to the origin. Do not, be careful. Warning, warning, warning. Do not start your angle at the origin. You want to start it close to the origin. So start it about right here. All right, now let's think. This is whole numbers, 5 pi. Watch. Is that going to be a positive or a negative rotation? Positive. Check this out. That's 1 pi, right? 2 pi, 3 pi, 4 pi, 5 pi. Do you guys agree with that? Do you see what I did? Now look. Look right here. I have to count it off in singles. I don't know why. I just do. 1 pi, 2 pi, which is 1 revolution. If I went another revolution, it would be 4 pi, 5 pi. Did you see it? Some of you will be able to count it off. 2, 2, 4, 5. Some of you will be able to do it that way. I can't do it that way. I can't, but you can, and that's fine. Do you see what I'm doing? That is showing the angle 5 pi radians. And yes, you have to draw the rotation. It's beautiful and fun. Some of you will have a blast with this. What's that terminal point right there? Negative 1, 0. That's it. Facile, huh? No. 2.5 revolutions, yes. And see, your brain's going to go there. 720 plus 180 is 900 degrees, yeah. Attaboy, Easter. High five in the air. See, weirdo. Let's do this one. I say that with love. Does that matter? Check this one out. Graph negative pi and find its terminal point. That's good. So draw your coordinate plane. Is this going to rotate up or down? Down, and this is 1 pi, so I'm going to start here, and I'm only going to go 1 pi. That's half of a revolution, isn't it? Because a complete revolution is how much? 2 pi. What's that terminal point? Shut up. What the world? What's going on here? Nope, not everything. What are you noticing? Go ahead, Christian. You always start your angle here at 1, 0. Yes, sir. Always. What did I do? What do you notice here? Not what I'm looking for. Well, that doesn't change. You always start at 1, 0. You always start on the right side of the x-axis. It has to start there. The odd numbers always end up on the x-axis. Yeah, that's true. That is true. If they're whole numbers, they do. Okay? Something else. Look at the terminal points, y'all, for both of these different angles. We drew 2 different angles, did we not? But they share what? The same terminal point. Now, is that always going to happen? In some cases, that's always going to happen. We'll go over that in a couple, maybe next week. But I do want you to make this notation. Although the terminal points are the same, the angles are not the same angles. Because we're talking about numbers of revolutions. 900 degrees is definitely not the same as negative 180. Do you agree? They are not anywhere near the same. But they'll take you to the same place. Kind of like, and I use this analogy a lot, I can get to my house a whole bunch of different ways. I can go straight down 58, boom, I'm home. Or I can go to Sandy Ridge and cut through the country. It'll take me a whole lot longer, but I can do it, and I can get home that way. Do you understand? It gets me to the same point, different ways to get there, okay? Now, check this one out. I want you to do this one. These two, and I want you to do them fast. Graph 6 pi and give me the ordered pair, the terminal point, and then I want you to graph negative 3 pi over 2. Go. 6 pi. Monica. I'm going to rotate up or down? Up. All right, here we go. Did you count this by 2s or 1s? 1s. All right, so 1, 2, 3, 4, 5, 6. Yes? How many of you had 3 rotations? You got to show the 3 rotations. What's our terminal point, everybody? 1, 0. High five. Boom. Thank you. Negative 3 pi over 2. MC, you made eye contact. Am I rotating up or down? Down. How'd you count this off? You went halfway, so 1/2, 2 halves, 3 halves. How many of you had that right there? Ah, those are the tricky ones, and that's why I told you. Whatever that denominator is, you count by halves. 1/2, 2 halves, 3 halves. Ah, what's that terminal point? 0, 1. Very good. How many of you had that? Yes. There we go. All right. Now, we have dealt with even numbers, whole numbers. 1 pi, 2 pi's, 3 pi's, 4 pi's, right? We've dealt with pi over 2 angles. What do you think the next logical place would be? We've dealt with 0, 90, 180, 270, 360. What would be the next logical place to go? What do you think? What? Oh, cute. Are you reading my notes? Have you, like, stolen my notes, made copies? What happens when the terminal point is determined by 45 degrees? Now, 45 degrees. You know what you're going to do. You're going to draw a big old unit circle. Yes, another one. These are now the days of taking 73 pages of notes every class. And you will like it. Yes, you will. I saw your faces. 45 degrees. Huh. Does that line kind of mimic a 45-degree angle? Are you buying that? Yeah? Can I draw another one this way? That's breaking that thing up into 45-degree increments. Yeah? We can't think in terms of degrees. We've got to think in terms of radians. So what fraction? We've dealt with whole numbers. We've dealt with halves. What fraction is going to represent a 45-degree angle? Oh, pi over 4. There we go. Pi over 4. That's what somebody asked first block. It does. We don't deal with those. What we'll go over tomorrow has to deal with thirds and sixths. Pi over 3 and pi over 6 angles. We'll deal with those tomorrow, but that's why I keep it all separate. Today is today. Tomorrow we worry about those, okay? Now, pi over 4 is exactly right. 45-degree increments. That's what you've got to think. 45-degree increments. So we're talking 45 degrees, 90 degrees. What's the next one? This just helps us think. 135, 180, of course. What's the next one? 225. 270 doesn't change, does it? But it's an increment of 45. What's this one? 315. And 315 plus 45 is 360, right? And I should have put a 0 up there. Now that's thinking in terms of degrees. But we've got to have, we ain't dealing with degrees anymore. We're dealing with radians. So what is 45 degrees going to represent? If this is 0 radians, 45 degrees is going to represent pi over 4. All right, now think in terms of, what earlier we thought in terms of whole numbers and halves. Now we're going to think in terms of fourths, okay? So I've got 1/4. What's this going to be? 2/4. Oh, but wait, it reduces to what? That didn't change. Okay, but think, 2/4. What's this next one going to be? 3/4 or 3 pi over 4. And the next one would be 4/4. Oh, but hold on. That's really just pi, isn't it? What's the next one? 5 pi over 4. You guys cool with this? Thinking in terms of fourths. We keep rotating and it's 6 pi over 4, but wait. That's really just 3 pi over 2, isn't it? And then we keep going. So we had 6 pi over 4. What's 3/15? 7 pi over 4. And then 8 pi over 4, which is really just 2 pi. Do you understand why I keep telling you think in terms of fractions? I promise. Y'all know I love fractions, and I would not do this as a cruel joke to you. I promise, because I know how y'all kick and fight against fractions. But if you will think in terms of fractions when you are labeling this, because remember, we still got to deal with thirds and sixths tomorrow, all in the same unit circle. It is going to be a jumbled up mess. And if you will think in terms of pi over 4, 2/4, 3/4, 4/4, 5/4, 6/4, 7/4, it'll help you in the long run, okay? Now, we got to talk about terminal points. We've dealt with 0 radians, and we know that 0 radians is 1, 0, right? We know that. But what's the terminal point for pi over 4? We're getting ready to do a proof without doing a proof. What is this line, this dotted red line? Does that look familiar to any of you who just came out of Algebra 2? It's linear. What? Parent graph. Yes. That's a right. Yes. Y'all remember that? That right there is the parent graph for the linear function y equals x. Atta girl. Yes, you were told that. You were actually given a paper on it. All of y'all were. You shouldn't. That means you never learned. Y'all got a paper because Dr. G gave me the paper. Promise. Parent graphs of the linear functions, parabola, the quadratics. Promise he did because he gave me the worksheet. I promise you got it because he's the one that gave it to me. You remember that sheet, don't you? Okay, the parent graph. Now look, real quickly. This will go fast. The parent graph, that function is y equals x. So that means when 0 is x, the y value is 0. When the x value is 1, the y value is 1. 2, 2, 3, 3. 4, 4, and on and on and on, right? It's a straight line. It's the parent graph. It is the mother and father of all linear functions. Here we go. So how's this all going to tie into what's the terminal point of the pi over 4 angles? Getting ready to do a proof without doing a proof? Oh, yeah. What's the only equation we have at our disposal right now to help us find ordered pairs? X squared plus y squared equals 1. We're getting ready to derive the ordered pairs for pi over 4. You want to put that over in your margin. Well, if the x term and the y term is the same, then can't I substitute and say x squared plus x squared is 1? Because if x is, according to that function, it said y equals x, didn't it? So whatever the x value is, the y value is. Do you agree with that? So we substituted. Now, folks, now it's just algebra. What is x squared plus x squared? Oh, yes. You know I'm waiting for somebody to go, 2x to the fourth. Please don't do that. Now, how am I going to solve this? Divide by 2. Come on now. X squared is equal to 1/2. What do I do now? Square root of both sides. Look what's going to happen. X is equal to, be careful, plus or minus. What's the square root of 1? 1 over the square root of 2. Can I leave it like that? No, rationalize. Got to rationalize. Multiply by the root 2 over root 2. And it's going to give you x is equal to plus or minus root 2 over who? Plain old 2. So my x values for all of my terminal points for the pi over 4 angles are going to be what? Root 2 over 2 every single time. Are my x's equal to my y's? Yes. So what will my y values be? The same thing. Since my y equals x because of the parent graph, then all of my y coordinates equal plus or minus root 2 over 2. Write that down. This is part of our proof without being a proof. Okay? Since my y equals x, because of that parent graph, then all of my y coordinates for these terminal points will also be root 2 over 2. These are the second easiest terminal points to know because they're the same. Okay? Now, go back to your unit circle. Go back to the top. Be mindful of the quadrant in which these angles lie. The first quadrant's positive, positive, isn't it? So that terminal point is root 2 over 2, root 2 over 2. Quadrant 2, terminal point for 3 pi over 4 is going to be what? And positive, root 2 over 2. The numbers are the same. The only thing that changes are the signs. The angle 5 pi over 4, that terminal point's going to be negative, negative, right? So negative root 2 over 2, negative root 2 over 2. And then 7 pi over 4 is going to be root 2 over 2, negative root 2 over 2. Do I have to memorize these? Yes. It's easy. Folks, and when this is all said and done, you're actually only going to memorize the first quadrant. And then you're going to see something happen, and that's all you got to remember, okay? And you'll see that in the next couple of days. But you're going to have to know this terminal point, root 2 over 2, root 2 over 2, okay? And think about it. Go back to geometry, right triangles. The 45, 45, 90 triangle was what kind of special right triangle? It was an isosceles. An isosceles triangle has 2 congruent angles and 2 congruent sides, right? Does this have 2 congruent values? 45. Make that connection back to geometry, okay? Make that connection. Here's something else. Tell me when. All right? So, I don't care what that clock says. So we're going to find the terminal point of following angles. We're going to do the same thing. Draw the rotation. Give me the ordered pair. Okay? I want you to draw and give me the ordered pair for the angle negative pi over 4. Now, you got to draw it. So you know you're going to have an x and a y axes. But there's something else you need to draw that will be beneficial to you. You need to draw. I wouldn't even draw them as dotted lines. I'd draw them as just straight up lines. Do you guys see how I tear up my colors? Some of you will need and want colored pencils for this, or markers, which are back there. Colored pencils are back there too. Folks, for pi over 4 angles, draw the perfect x. Okay? You will understand about the perfect x, because tomorrow we're going to talk about a skinny and a fat x, which will just be helpful to you when we draw these angles. But for pi over 4 angles, draw the perfect x. It'll help you, okay? Let me show you why it's going to help you. Am I rotating up or down? Down. So we start at the x-axis and we rotate 1/4. Boom. There we are. Do you guys agree with that? Bless you. What's that ordered pair? Root 2 over 2 and negative. There we go. Facile or difficile? Bless you. That's pretty facile. That's not difficult. Don't think that it is, because it isn't. One more. Can I move this page? Because I'm running out of room. All right, here's another one. I want you to graph 7 pi over 4. And determine the ordered pair, the terminal point. We're going to count this off in terms of what? Fourths. Rotate up or down? Up. All right, check this out. If you're unsure, watch. Watch what I do. I'm going to have to count how many fourths? 7 fourths. 1, 2, 3, 4, 5, 6, 7. Do you guys agree? Okay. What's that ordered pair? Say it, Morgan. Right on. How many of you get it? Excellent. High five. Here's another one. Last one. Negative 5 pi over 4. See what you come out with. Start at the x-axis. 1, 2, 3, 4, 5. How many of you graphed that rotation correctly? Ordered pair, what is it? Negative root 2 over 2, positive root 2 over 2. How many of you had all of that right? Facile or difficile? Is it getting more facile? Okay, that's all I care about. Here's what you're going to do. Folks, page 120. Guess what? We're on 120 again. You're going to do the following problems in just a minute. I just want you to remember that your pi over 2 angles are in terms of what degree increments. Pi over 2, what degree? Pi over 2, think. See your unit circle. 90-degree increments. Please write this down. Just to review. pi over 4 angles are in terms of what degree increments? 45-degree increments. When you wrap your head around that, this will become a piece of pie for you. I know. Okay, see, I was calm. I was pretty calm. I want you to do page 120, numbers. 910, 1420, 25A, 31, 35, 38, and 42. And look, I don't care what the instructions tell you. I do not give a rat's hind end what they tell you. This is what you're going to do. You're going to draw the angles, and then you're going to determine the ordered pairs. Exactly what we just did. And when you see the last 2 or 3 problems, it's going to make you cry. And I just think it's funny. You'll be all right. You will be fine. Okay? The bigger the numerator, the closer into the origin you start with your angle. And you'll rotate and rotate and rotate and rotate and keep on rotating until you get there. Have fun with that. I've had to do it. Now it's your turn. Okay? Get on it. Use your time.